Okay, so when you guys look at your foldable that you have and the information that you have, some of the things that I want to draw your attention to is these arrows in the middle, okay? And that is in the middle portion of the mantle, also known as the asthenosphere. So middle portion of the mantle is the asthenosphere. If you don't have that correct on your diagram, you're going to want to double check that. The other difficult one that I noticed was that this top portion, the upper part of the mantle, and then including the crust, that is the lithosphere. Your guys' drawing also includes crust on this side, which I'm going to draw in real quick because it is important to emphasize that. What is that crust called? Adam?
Oceanic.
Yeah, it's the other section of the oceanic crust. And so we do have oceanic crust below the continental crust, and that's really important to remember. There's a concept we're going to talk about today that ties into this motion or this effect that we see within the mantle. And we're going to start with talking about density. So what is density? What do you know about density, and what are some properties of density? That's what you're going to start talking in your groups about. Okay, go. To summarize some of those main points, and you can record this on the back if you would like to, because this is going to play a role in how you understand the mantle convections in particular, and then some other things that we're going to talk about as far as shapes of the Earth's features. So density, we started out with, density was, if we were to put in a formula, density equals mass divided by volume. Okay, so M is mass, and V is volume. So it's how much mass we have per little space or per volume of space. If I were to draw out a diagram, and usually this is three-dimensional, but you guys know my drawing skills, so this might be more confusing when I do this than helpful. And I was to draw some particles into those spaces, so these are little atoms, little particles, right? And they're three-dimensional, so it's filling up the whole thing. Versus something that looks maybe like this. What are some things you could say about these two boxes as it pertains to density? Go ahead and talk at your table first, and then we'll share some ideas. Okay, so we could say this one over here on the right-hand side maybe is more dense. Okay. What else could we say about those? Will? Okay, so more dense, we see that they're more compact. Would it be fair to say less space between particles, Will? Okay. Adam?
Volume and different mass.
Okay, so volume in both is equal. And what did you say about mass?
They have different masses.
Different masses, meaning what?
The left one has less mass because it has more air in between the atoms.
Good, less mass, more mass. What I like about what you're talking about here, Adam, is the formula, the whole definition behind density, right? So it's mass per volume. The volume's the same, so that's not a factor, right? It's equal for both of them. But this one has less mass, and this one has more mass, meaning more particles. What is mass? How do we define mass? Joe?
It's stuff.
Get a little more specific. It's stuff. But stuff where, Andrew?
It's like the measurement of the matter.
Okay. Will?
It's like anything that takes up space.
Well, matter is anything that takes up space, and mass is how much stuff is inside something, right? Or that something is made of. So, yes, it's stuff, but be specific. So in this case, mass is all the stuff that makes up those blocks, right? So we have mass that takes up a space, the space is the same. If there's more stuff inside a small space, then it's more dense. And then that tends to have an implication on whether it sinks or floats, as Andrew mentioned in our discussion. So if it's more dense, it's going to sink. If it's less dense, it's going to float. And that plays a vital role, just even how our continental crust and our oceanic crust is in proportion to each other. So if continental crust is on top of oceanic crust, what does that have to say for their densities? So when we look at this, we see our oceanic crust is made of what? What did we say that was made of? Basalts. And remember that the oceanic crust is at the bottom or the base, and it's made of basalt. That's how I kind of remember which is made of what. So oceanic crust is at the base, made of basalt, and then our continental crust is at the top, and it's made of granite. And the whole reason why they're arranged in that manner, granite on top of basalt, has to do with their density. It's not that, oh, hey, we're just going to make continental crust out of granite, and it's just going to happen to be on top of oceanic crust. There's science behind that. So the basalt is more dense, and granite is less dense. So we have to take this factor a little bit further. Thinking about density even more, when we talk about these arrows in the middle, you guys should have a label on them. What are those arrows labeled as? What is that representing? Izzy? Good, convection currents. So I'm going to throw my label in here that these are my convection currents. We know that this basalt layer is dense. It's very dense. And I tell you that the mantle itself is less dense than oceanic crust. I'm just going to abbreviate that as OC, as the oceanic crust. What implications does that have for something or a motion or even a process that would happen? Okay, so what implications does the less dense mantle lying underneath a more dense oceanic crust have on what happens to our crust and our mantle? Talk at your tables first. Okay, so what we're going to look at then is if we have something that's more dense sitting on top of something less dense, we know that things that are more dense sink below things that are less dense. So why is it that our earth is not collapsing? Why is it that we don't see just that top layer falling down past that middle layer? Or even more so, how does this even tie into the fact that there's convection currents there? So just focusing on those top two layers, and again, focusing on the arrows to start out. Whenever we have something more dense on top of something that's less dense, we are going to have sinking. Okay? So what we see is, we see this layer of oceanic crust, and I'm going to draw this other side back in because we want to see both sides of this. We see the layer sinking downward at a plate tectonic boundary. Okay? And as that piece sinks downward, something happens to the temperature of it. What happens to the temperature of our Earth as we travel further towards the interior? Good. So as we go down, we see heat increasing. Let me get a different color here so that I can depict that. As we travel down, we have the increase of heat. And one known fact about hot things is they don't sink, they rise. So heat rises. Think about attic spaces in your homes. If you've ever been in an attic, you'll realize it's really, really hot up there because all the hot air is rising. Okay? It's the reason why a lot of people run ceiling fans even in the middle of the winter. They put them in reverse to push the air down, so the hot air that goes up gets pushed back down. So a lot of people use that as a technique to to heat their homes a little more efficiently. But hot air rises and cold air sinks. Okay? So if that's the case, as this hot hot oceanic crust is sinking, it melts because it's a lot hotter in that mantle. And then that melting, as it continues to sink, it gets hotter. But as it gets hotter, it wants to do what? It wants to rise up. So that's one of the processes that we're going to focus on. We're going to focus on this current that is caused as a result of this more dense oceanic crust sinking. And then as it sinks, it's heating up. Then what happens? So you can add this to the behind the flap if you want on the mantle, or you can even add this to the front side of the flap. But go ahead and put it somewhere where it's easy for you to see and easy for you to review for your quiz next week. So we have down at the bottom arrow, things are heated up. And when they're heated up, they rise. So hot material rises. So this bottom arrow is that hot stuff. It's all hot. It heated up from falling. And all of a sudden it starts rising. When it gets back up to the top, so as it's rising, what starts to happen to that material? Good. So the hot material rises up and it starts to cool. So it cools down. So again, that cooler material, cold things sink. So as it starts to sink, what starts to happen again? It heats up. So this arrow coming down is cool material sinks. And then it heats up again. But it all ties back to density. Cool material is more dense than hot material. So think about the particles, the individual particles, as something goes from a solid to a liquid. Okay, solids, you have material that's really, really close together. They're closely packed together, and they're in this definite shape. You learned about that in 6th grade. So that dense, closely compacted material sinks into the less dense, more spread out material. Okay? And as it sinks, we know the interior is hot, heats it back up. Okay? And then all of a sudden, as it's heating up, it rises. But as it rises, it's cooling, making it more dense. So it's a combination of two factors. The mantle itself, or the convection currents themselves. What are those two main factors? So the reason we have these convection currents so these guys is due to one, I'm going to say density first, kind of a chicken or egg type scenario though, and number 2, the temperature. I'm not going to just say heat because it could be the absence of heat. Remember that as things cool, it's losing heat. As things heat up, obviously they're gaining heat. So it has to do with the temperature and the density. So with that thought in mind, my next question to you then is, what's happening here at our surface? Because we study Earth's interior as a way to help us understand the things that we can see or the things that maybe impact our lives. Where do we live? We live up here, right? So here I am hanging out up here, you know? And there's a reason we care about all this stuff below us, though. So what implication does this whole current that's happening down below us have to do with us up here? We have this shifting of these plates, and they're grinding together and sinking down into the mantle because they're more dense. It's going to cause earthquakes. Good. So we could have volcanoes. But if this piece is moving towards this piece, what's happening on the backside here? Joe?
It's being pushed this way or getting turned.
Yeah, so it's kind of getting pushed away. So for 1 second, let's add in another convection current because there's thousands of these around the entire sphere of the earth. So on this side, then, if we were to continue our arch over, right, and continue drawing our circle of cutting the earth in half, on this side, we have that hot material rising, cooling down. Because it cools down and becomes more dense, it sinks, and then it heats back up and rises. Which means there's a plate over here on this side that would be lined up. And instead of moving towards each other, what's happening to those plates? They're moving away. Because what you have are these two pieces and a convection current pushing it away, right? So these two are coming towards each other. And then these guys are moving away from each other. So we have some spots of our Earth where plate tectonics are moving away from each other and some spots where they're moving together. So overall, that has a drastic effect on where our continents are located. And there's lots of evidence over millions of years what Earth looked like millions of years ago as opposed to today where those continents are located. And then there's a lot of implications as far as different features that we have. Mountains, right? We watched a little video clip of the Himalayas and the formation of those Himalayas as those plate tectonics move together. And all of a sudden there's this massive mountain formation. We also have implications as far as if they're moving apart. If you're standing on two sections of the Earth that are moving apart, it's kind of dangerous, right? So earthquakes, volcanoes, all of those processes are going to play a role in how our Earth is shaped. The features that are there, the resources that are available, and we're going to really dig into that this year. So I want you to take a look at one more factor here and go ahead and draw this in. If our oceanic crust is more dense than our continental crust, I want you to draw it in with your particles. So you got particles maybe closely packed together on the oceanic crust. Okay, as opposed to maybe loosely packed for the continental crust, and I'm going to draw this as an extreme. Obviously, they're not quite this drastically different. But then we also have in our upper mantle much loose or more spread out packing of those particles. And then that's going to be that major initial driving factor. When you describe a convection current, you're talking about the more dense material sinking into the less dense material. At the same time, we have an increase in temperature because we know that that heat is so high towards the center of our Earth. And then all of a sudden they become less dense, so they rise back up, cool material rising back up because it's less dense. And then it becomes more dense again as it cools at that surface. Okay. The last factor that you need to draw in there, and you can draw this all the way down the one side of your diagram, is what happens as we travel to the center of the Earth. We've already said one, so draw this all the way down from the crust layer, just right over the top of all your flaps. If something is not only heating up, so we know it gets hotter as we travel to the center, there's another factor that's going on. It's the reason why the very core of our Earth is solid. It's the hottest portion of our Earth, but yet it's solid. So what is that factor? Pressure is a major factor. So not only do we have heat increasing as you travel to the center, we also have pressure increasing. So as you get to that very center portion of the Earth, we have that really tightly packed ball of iron and nickel. And I didn't necessarily talk about the two components, iron and nickel. They're both there at the core, and they're there at the inner core, and they're there on the outer core. But the outer core is a liquid, and our inner core is a solid, and it all has to do with the pressure. So the amount of force pressing inward is what we're referring to there. So let's take a look one more time at that little video clip and the different motions that we see. So again, this video starts out by showing us that inner core, that solid sphere, high pressure, okay, very solid. And then we have our convection currents. So we have that material rising up As it rises up, it's cooling down. That cooling down material becomes more dense, starts to sink, and as it sinks, then it falls down. I'm going to pause the video for a second. Falls down, heats up again, right? And that cycle continues. And then this part of the video is showing us what? What's happening? Say it louder.
The earth changing.
Okay, so the earth is changing. Those plate tectonics are shifting and moving. So while this is all happening inside of our earth, there's things happening to the outside of our earth as well. Okay, so make sure you review your foldables and the information on it. There's a lot of details in these foldables. They're the outline or the graphic organizer that you'll use for your quiz. But then the other thing I want to point out is a lot of this basic information we just talked about ties into a lot of factors that we're going to talk about throughout this year. So you're going to need to be able to reference back to this quite frequently. So keep a hold of this, make sure it's in a safe place. Okay.